Hello and welcome to our lesson on inverse, tangent, and reciprocal functions. So really what we're going to do in this topic is the same thing we did in the last topic. We're going to look at the rest of the inverse trig functions. Now remember that all of our trig functions are periodic functions, which means that they aren't going to be one-to-one functions. Therefore, not one-to-one functions. And in order for an inverse trig function to exist, it's, if the inverse, in order for that to be a function, then the original function we're looking at has to be one-to-one. So to make this work with our trig functions, we're going to restrict the domain. Since our periodic functions are not one-to-one over their entire domains, we're just going to restrict to a specific domain so that we're looking at an interval that is one-to-one that also captures all of the behavior of that particular trig function. So if there's a max or a min or a certain set of y values that happen, in that periodic repeating pattern, we want to capture all of those, just don't want to repeat them, okay? So let's look at the last four that we have to cover. Hopefully we're recognizing some of these graphs. Let's talk about the first one here. Now maybe it's easy to get these two confused, so remember where they're coming from. If I was to draw the reciprocal behavior in here, this first one, then that reciprocal behavior represents our sine wave. So I know that this graph represents the reciprocal of sine, which means it's my cosecant graph. So what we're looking at in this first picture is y equals the cosecant of x. Okay, that's our parent cosecant, and this would be one cycle of it, centered around the origin from negative pi to pi. Now this is one cycle, but again, this does not represent a one-to-one function. There are plenty of places where we fail the horizontal line test. So like we did yesterday, maybe we start at 0, although that's going to be impossible in this one because we have an asymptote there. So right past 0, we're approaching 0. If I was looking to capture all of the values I see and still look at a one-to-one function in the cosecant graph, I would be totally fine for this piece of the graph here over this interval, but as soon as I turn over the vertex of this parabolic piece, I'm not going to be a one-to-one function anymore. So this little piece that I have captured does represent the positive ratios that I would see for my cosecant function, but I also need to capture the negatives, which I see on the other side of the asymptote. So this would be the positive here. The other piece of this would be the negative ratios, which I can find here. Now I don't, again, want to turn the corner because I would not be a one-to-one function if I turned there, but also I've already captured these values on the other side. So these outputs are already captured here. So if I'm looking at these two pieces of the parabola, the two parabolas on either side of that asymptote, I'm capturing all the y values that are going to exist on the cosecant function, but I'm not repeating them, so that little section is one-to-one. And so if I restrict my cosecant function to that interval of x values, then the inverse cosecant function will be directly connected to that interval. So we're going to see the restrictions happen in reverse there. So we're going to restrict to negative pi over 2 to pi over 2. So we're going to say the domain, and that is my highlighter. The domain for the cosecant that we're going to restrict to is going to go from negative pi over 2 to pi over 2. However, I can't go directly there because of the asymptote that's in the middle. So I'm going to go, and maybe I should write this not here. This is not going to be enough space. So let's call this y equals the cosecant of x. And let's say its domain is going to start at negative pi over 2, and it's going to approach 0, but because it can't get there, we can't include it. And then we're going to unite that with, again, we're approaching 0 and then going toward positive pi over 2. So this is how we say that we want the angles between 0 and negative pi over 2, and then again 0 to pi over 2. So we just want to exclude that 0 because of the asymptote. So that's the domain there. And then the range being opposite of our sine. Remember, the sine is in there from negative 1 to 1. Here we see the parabola going from positive 1 up to infinity. And here we see the parabola going from negative 1 down to negative infinity, or negative infinity up to -1. So outside of the range that we see for sine. So everything from negative infinity up to -1, united with everything from +1 to infinity. Now, if this is the domain that we're restricting to, that's our range, we know that when we're looking at the inverse of our cosecant function, the inverse cosecant function, those two things will be switched. Okay, so let me take you to Desmos for a second. Here's our cosecant, restricted to the domain that we just said. We're going to go from -π/2 to π/2, but we're going to exclude that asymptote at 0. And now if I actually ask Desmos to graph my inverse cosecant function, you're going to see what popped up there in blue. And again, sort of segmented like a little piece of a graph. That's because the restrictions that we applied to our original function do directly impact what we have there. And notice also we have the symmetry in those two graphs over the line y equals x. So we have the inputs and the outputs switching, the domain and the range switching, but restricting our original to a one-to-one function so that the inverse still represents a function. Okay? So let's do this again. Let's go on to the next one. We know this one now is cosecant, which means this one's going to be secant, but again, hopefully you're seeing your inverse behavior here. So this would be like this. Trying to follow this, reciprocal behavior. Sorry, let me mind my language. If I sketch my cosine wave in there, I see my maxes and mins of cosine being the maxes and mins of those parabola, the vertices of those parabolas. And so since I see my cosine wave in there, I know that this function is the reciprocal of cosine, and the reciprocal of cosine is secant. So this represents the secant of x. And again, what we want to do, even though I have one cycle here graphed over the interval from -π to π, we want to restrict this to a one-to-one portion, but also capture basically the same thing we saw in the last one, right? Make sure we get the positive values, the negative values. So maybe we start at 0, right? If I started at 0 and I went this direction, I would be totally fine here. Now, if I went backward from 0, which sometimes is an option, like we did that over here, we went on the other side of 0, then I'm not a one-to-one function, so I don't want that piece. But from 0 here, I'm good. Now, I do have an asymptote in this graph, which is totally fine. I can exclude that from my domain. If I go over the asymptote, then I have the negative ratios that I would be looking for. So if I restrict this to 0 to π, excluding the asymptote that's in the middle, then again, I've captured the positive ratios, I've captured the negative ratios, all the outputs that are possible for secant, but in a one-to-one interval. So we're going to say the domain that we're going to restrict secant to is going to start at 0, end at π, but we have to kick that asymptote out. So we're going to go from 0 to π/2, and we cannot be equal to π/2. There's an asymptote there, so we're going to put parentheses on that. And then again, we're going to pick up at π/2 and then go to +π. And we're defined at the ends at 0 and at π, but not at that asymptote that's in the middle. And then the range, again, everything outside of or above +1 and below -1. So we're going to go from negative infinity to -1 and then unite that with everything from 1 to infinity. So if these are the inputs for my secant, they're going to become the outputs for my inverse secant. And if these are the outputs for my secant, those will become the inputs for my inverse secant. Okay, keeping in mind again that the outputs for the inverse trig functions, which we're going to be evaluating in just a few minutes, those are angles. Okay, so now let me show you in Desmos. Here is our secant, restricted to that interval that we said from 0 to π, kicking out the asymptote that's in between. And if I look at the inverse secant, there it is. Now it looks a little strange, but that's exactly the effect, right? That is the symmetry over the line y equals x. If I reflect, change all those inputs and outputs. Again, it's a weird looking segmented piece of the graph, but it does in fact have that symmetry. It looks a little... It's really hard. There we go. If I square this, it's a little bit easier to see, but there is definitely symmetry over that line. Okay? And time for the next round. So we've taken care of the reciprocal of sine, the reciprocal of cosine. Now let's look at our last two, which are tangent and cotangent. It's reciprocal. So this one, I don't know if you remember which one's which. It's been a little bit. So this one's going to be our tangent. So tangent is centered at 0, and tangent is increasing. Where cotangent not centered at 0. Um, the first in our first iteration of the unit circle lap, we cross at pi over 2, not at 0. But we also have decreasing branches here instead of the increasing branches. So this is our tangent function. So y equals the tangent of x. Again, not one-to-one over its entire domain, so we're going to restrict it. If we want to capture everything that's happening with tangent, just not repeat those y values, then I think this one cycle, we have the positives here. I don't want to go over the asymptote if I don't have to, and I can capture all of the values, the positives and the negatives, in one fluid branch there, one continuous branch. And so we're going to use that one cycle that already goes from negative pi over 2 to pi over 2. So we'll just restrict it to that interval, that one cycle that we normally look at. So we'll say the domain that we're going to restrict tangent to is for its one cycle that we see happening from negative pi over 2 to pi over 2. Now keep in mind that outside of that branch of that graph, we do have asymptotes. And so in this domain, I have to exclude pi over 2 and negative pi over 2. All right, so there's our domain. And the range, we see this graph go up and down forever, so we have an infinite range, which means when we go to look at the inverse tangent, we're going to have an infinite domain. So here we have any infinite number of options for outputs. For inverse tangent, any infinite amount of inputs are going to be possible. All right, let me show you. So here's our tangent, just that one cycle from negative pi over 2 to pi over 2, which captures the whole essence of tangent there. And here's the inverse. And again, reflection over the line, y equals x, switching all those inputs and outputs. So we go from the infinite range to the infinite domain. Okay. Last one being cotangent. So again, we know this as y equals the cotangent of x. We don't want the cycles over and over and over, right? So again, we have an asymptote right here at 0, so I can't start there. But I could start here and then continue following this branch to capture everything, every output that's possible for my cotangent function. So if I just take the one cycle of cotangent, that's going to go from 0 to pi, of course excluding 0 and pi where we have the asymptotes, then we have an interval that is 1 to 1, and again captures everything that's possible in terms of outputs for cotangent. So let's restrict cotangent to its one cycle that goes from 0 to pi. Again, not able to include 0 or pi in that because there are asymptotes there. And then our range, just like tangent, these graphs go up and down forever, so infinite. And then the opposite will happen for our inverse. So last set. Here's our cotangent, that one interval from 0 to pi. Here's the inverse. And again, symmetry of those two graphs over the line y equals x. Okay, so we went from the infinite range to the infinite domain, and all those inputs and outputs are switched. Okay, so by definition, what we see in the table is exactly what we just decided in all of those restrictions. So if we're looking at inverse cosecant, that was the first box, because the domain here goes from negative pi over 2 to pi over 2, but kicks out the asymptote in the middle. That's what we see happening for the range here. And then we see that the range here from negative infinity to negative 1 and 1 to infinity, that becomes the domain here. Right? And it's the same concept all the way throughout. So we're going to switch the domain and the range because we're switching the inputs and outputs for all of our inverse functions. So if we switched everything we wrote up there, that's what we see defined in our table. And then remember, we have two notations for inverse because this is really easy to confuse with an exponent, and it is not an exponent. This does not mean the same, so not equal to 1 over cosecant. We know that's a reciprocal, it has another name, because that gets or could be confused with an exponent. We have this other notation. So inverse cosine with the negative 1 or the inverse cosine. Inverse cosecant or arc cosecant, two notations for the same thing. Those are both the inverse of cosecant. Okay, so same stuff that we saw yesterday, but just now all of our definitions all in one spot. So eventually we'll be using some of these concepts to solve, but what we're going to try next is what we were doing again in our previous topic, and that's evaluating. So when we're evaluating, I'm asking you, for instance, to find the exact value for the arcsecant of 2. Remember, the output of our inverse trig function is an angle. So we input angles into our trig functions, which means we get an output that is an angle for our inverse. So when we're evaluating here, we're looking for an angle. We really just have to be careful to make sure that the angle we're looking at is in the range of angles that's allowed for our inverse, and then also that the input that we're plugging in is in the domain. So make sure we're in the applicable range or domain. And then when it's possible, we're going to use the unit circle to find exact values. If it isn't possible, or if we want to verify, then we turn to the calculator. Okay? Now, if you'll notice, I broke this up on your note sheet into 4 sections. That way we can highlight and not have to make too many highlights like on one unit circle. We can highlight the different ranges for the different inverse functions. So let's start with the inverse secant. So remember, secant, over here, remember that secant is the reciprocal of cosine. Oh, I thought I was going to sneeze. It didn't happen. Okay, so secant is the reciprocal of of cosine. Oh my gosh. It's really, I don't know why this happens to me every evening. It's because my allergy pill is wearing off. I think that's what's happening. Okay, sorry. Secant is the reciprocal of cosine. So when we're looking for our angle, keep in mind we're going to have to take the reciprocal of the cosine value. Okay, so secant's the reciprocal of cosine, but also when we're looking at, is that what I try to put these in the same order here. No, see, I wanted to go in that same order, but I didn't. It's fine. So the reciprocal of cosine. So before I do any work here, I have my own unit circle dedicated to this little section. So when I'm looking at cosine and its reciprocal, our range of angles is almost the same, okay? For cosine, let me go back to my table here, and for its reciprocal, which is secant, we are going from 0 to pi. We just have to, on the secant, kick out the asymptote that's in the middle. So cosine and its reciprocal are almost the same in terms of range. So here, when I'm looking at secant, again, reciprocal of cosine, I'm looking at the range of angles that goes from 0 to pi, but the difference here for the reciprocal is the 0 in the bottom of the fraction makes this one undefined at pi over 2, so I'm going to put that in there just to represent like an asymptote. So when I'm trying to evaluate here, I have to be taking an angle that is in that range, okay? So that's the picture I'm going to use now for these first 2 problems. So the first one, we are asked to find the arcsecant of 2. Remember, we're looking for an angle. So this means I'm looking for an angle such that when I take the secant of that angle, I get 2. Okay, now when I take the secant, I'm looking for the reciprocal of cosine. So I'm looking for a cosine value that has a reciprocal of 2. So where does the cosine have a reciprocal of 2? So cosine, change colors here. Cosines are my x values. So not a reciprocal of 2, not a reciprocal of 2. This has a reciprocal close to 2, but it's negative, so it's none of those. Maybe I should have started over here. Not a reciprocal of 2, not a reciprocal of 2, but there it is. Okay, so if I'm looking at this, the reciprocal of that cosine value is 2. That's the angle I'm looking for, which means my angle will be pi over 3. That's in the range where I'm looking. And I did not ask for you, Desmos. So then I'm going to go over here and say that my angle is, excuse me, pi over 3 radians. Okay? Number 2, given us as an equation instead of an expression, but same thing. If we're trying to find y such that it's equal to the inverse secant of negative 2 over radical 3, again, that means I'm looking for an angle. They're just naming it already for me. They're calling it y instead of me calling it theta. So such that the secant of that angle y is going to be equal to negative 2 over radical 3. So remember, secant's the reciprocal of cosine. I'm looking for, first of all, a negative cosine, which means it's got to be over here in quadrant 2. And I'm looking for the reciprocal to be 2 over radical 3. So if I take the reciprocal of negative radical 3 over 2, then it does in fact end up being this negative 2 over radical 3. So since that's what I'm looking for, this is my angle, 5 pi over 6. So we're going to say y is equal to 5 pi over 6. Okay, easy enough. Let's try it again here. In problems 3 and 4, we're looking at cosecant. And cosecant's the reciprocal of sine. So cosecant of x equals 1 over the sine of x. So we're going to look for the y value. Oh, I should have put that up here. Cosine's the x value, right? So technically we could say 1 over x. And sine is the y value, so technically here we could say 1 over y. However you're remembering that is totally fine. Alright, so now, because this is the reciprocal of sine, let's go over here and remember the range. Alright, we want to make sure we're in the right range of angles. So sine, if you recall, goes from negative pi over 2 to pi over 2. Its reciprocal does the same thing. The only issue is there's an asymptote in the middle. So that's going to be the range of angles that we're looking at here when we're trying to evaluate. So if I want to find y, which is equal to the inverse cosecant of 0, again, I'm looking for the cosecant of some angle, which they're calling y here, to be equal to 0. So I'm looking for the reciprocal of my y value to be 0. So where do I have a reciprocal y value of 0? Good question. Well, if I look at all these y values, I'm not going to be able to get a reciprocal of 0, right? If I try to take the reciprocal of 0, it becomes 1 over 0, which is undefined. Reciprocal of, oh, sorry, that's 1. I'm looking at my signs, which are my y's. Reciprocal of 1 is 1. This is clearly not going to get me a 0, neither is this, neither is this. Here, I'm not defined, so I could, I'm not defined there, so there's an asymptote. I can't even include that if I wanted to, but even if I wanted to, the reciprocal of 0 is undefined. Okay, so that's no good. So no matter where I look, oh my gosh, no matter where I look in my sine values in that range, I'm not going to be able to get a reciprocal of 0. So what does that mean? Well, it means that this is undefined, and it should make sense. So if I was looking at our cosecant function, remember the cosecant function, the range, right, the possible outputs for cosecant, which is what I'm looking at here, an output of cosecant, is everything above 1 and below negative 1. So this is not in the range of cosecant, and that means that this is not in the domain for its inverse. Okay, so I can go back to my table if you want to see it here for cosecant. So cosecant, my domain, my inputs, what I'm allowed to plug in, have to be from negative infinity up to negative 1 or from 1 to infinity, and 0 falls in the middle of that, so it's not in my domain, which is why I was not able to find an angle that corresponded. Okay, so what we would say about this value here is that it's undefined. And that's precisely what your calculator would say if you tried to verify. Okay? Oh, sneeze, finally. Oh, finally. Usually those elude me, and they just kind of bother me the whole time. I'm so glad that that sneeze finally came out. Excuse me, by the way. Alright, let's look at the next one. So number 4, we're looking for the arc cosecant of 2 over radical 2. So again, we are looking for an angle. An angle such that when I take the cosecant of that angle, I'm going to get 2 over radical 2. So cosecant, again, reciprocal. What am I writing here? Cosecant. Cosecant being the reciprocal of sine. So I'm trying to flip over one of my sine values and get 2 over radical 2. And it's positive, which means I have to be in the quadrant 1 and not the quadrant 4. And so if I flip over radical 2 over 2, then I get that 2 over radical 2. So there's where my reciprocal is 2 over radical 2, which means this is the angle. So we're going to call that one pi over 4. That's the one that's in range. So this angle is pi over 4. All right, moving right along. Next one we're looking at is tangent. So tangent, remember, centered around the origin, that one nice cycle from negative pi over 2 to pi over 2 is going to be what we're looking at here for its inverse. So the same domain that we restricted our tangent function to becomes the range of angles that we're looking at for inverse tangent. Now remember, this one starts and stops or has the tangents on the outside of that branch of graph, so there's technically an asymptote here. So we want to make sure that we're not doing anything with pi over 2 or negative pi over 2 itself. Okay? The rest is really the same concept. Now when you're looking for tangent, remember technically tangent, and let me go back to blue because that's what I was doing over here. We know that tangent is sine over cosine, or we take the y value and divide it by the x value. So however you're remembering that, either way is going to be fine. So we're trying to find in this first one here for tangent the arctan of negative 1. So we're looking for an angle such that if we take the tangent of that angle, we get a negative 1. That means I'm trying to divide my sine by my cosine, or my y value by my x value, and get a negative 1. So in the range we're looking at here, I got to divide something by itself to get a negative 1, right? The only way to do that is divide radical 2 by radical 2 over 2 by radical 2 over 2. Since it has to be negative, then I have to be looking in quadrant 4. So this is where my tangent, my y over my x, is going to get me a negative 1. So technically this is the location of the angle. But we saw this happen yesterday. We know that 7 pi over 4 is way out of range. To get to 7 pi over 4, I would start here. I'd have to wrap all the way around and then get there. That's not what I want. Now that's the location, but I need an angle that fits in that range of negative pi over 2 to pi over 2. So we're going to call this angle, instead of 7 pi over 4, we're going to call it negative pi over 4, right? Instead of going up pi over 4 to get there, we're going to rotate down pi over 4 to get where 7 pi over 4 is. So we're going to reclassify this as negative pi over 4. And technically, if we had landed here, this would have been negative pi over 6. And if we would have landed here, this would have been negative pi over 3. So if you wanted to use this better as reference later and just scribble those out, put the proper angle measurements in there, we'd be good. So for this one, we're going to say that our angle is a negative pi over 4. And again, that's because 7 pi over 4 is not in range. Okay, let's try the next one. Next one, we're looking for the inverse tangent of radical 3. So we're looking for an angle such that the tangent of that angle, which is called here y, is equal to a radical 3. So how are we going to end up with a radical 3 for our ratio? So you have to remember, so we're in this range, right? You have to remember what's the result of dividing some of these things. So we know that when we divide something by itself, we're going to end up with a 1. Those are the easy ones. If I took my y value and divided by my x value here, if I took radical 3 over 2 and divided it by 1 over 2, we know that these are going to cancel and get us that radical 3 that we're looking for. If I do this in reverse, so if I took the 1/2 and divided it by radical 3 over 2 instead, then I would have 1 in my numerator and radical 3 in my denominator. So this one, I was looking for positive radical 3. I found it. That ratio happens at this angle. So our angle is going to be pi over 3. So y is going to equal pi over 3. Okay, and now I have another one similar to something we saw in the previous topic. So I have the inverse tangent of the tangent of 7 pi over 6. So as we saw yesterday, these are opposite operations here. They do undo one another. So technically these opposite operations should cancel, and leave us this angle. But we cannot say that this is going to be equal to 7 pi over 6 because 7 pi over 6, not in our range. Now, I scribbled all this out. All right, 7 pi over 6 is over here. Oh, I didn't need to undo my scribbles. Let me put these back. Let me rename these. We said negative pi over 6 here, negative pi over 4 here, and negative pi over 3 here. Excuse me. So the tangent and its inverse opposite operations cancel. So they should leave us 7 pi over 6. But 7 pi over 6 clearly not in the range that I'm looking at. Now, what I want is for the same tangent value that 7 pi over 6 has. So if I'm to divide radical 3 over 2 by 1/2, I just did that work up here. Radical 3 over 2 divided by 1/2 is going to give me a radical 3. And this is negative, negative, so that would make a positive. So that the tangent here at 7 pi over 6 is equal to radical 3. So what I want to do is find an angle in range that has the same value. Well, that's precisely what we did in the last problem. So here, because 7 pi over 6 isn't a range, and also because pi over 3 has the same value, tangent value as 7 pi over 6, we're going to take pi over 3. Pi over 3 is in range and has the same value for tangent. So we're going to take pi over 3 because these both, or the tangent of both, is equal to radical 3. So they have the same value for tangent, but we're choosing the angle that is in the range. Okay? Alright, last set. We're looking at cotangent. This is the reciprocal of tangent. So cotangent of x, again, being the reciprocal of tangent, or being the cosine over sine, or being, x over y instead of y over x, right, is going to be what we're looking for on our unit circle. So let's start with, let's start over here. We have our own little unit circle. So remember our cotangent. Cotangent was kind of like tangent, except it's shifted over. So cotangent, the range, goes from 0 to pi, and there are no interruptions in that one branch. The only thing we have to be careful with is the asymptote when we start and stop that, or at the outside of that branch. So we can't include 0 or pi, but any of the angles in between, those are all going to be possible answers for these. So looking at number 8, we're looking for an angle such that if I take the cotangent of that angle, I get 1 over radical 3. So in the range, the 1 over radical 3, we saw that up here. That's going to happen when I divide a half by radical 3 over 2. So I want my 1/2 divided by radical 3 over 2, but remember it's cotangent, so that means in my x value divided by my y value, I want to have my 1/2 and my radical 3 over 2, right? So where do I have an x value of 1/2 and a y value of radical 3 over 2 and positive, so we have to be in quadrant 1, which means, highlighter please, we're going to be here. Same angle again, right? That's where I can take that 1/2, my x value, divide it by my y value, radical 3 over 2. There's my ratio for cotangent, and end up with 1 over radical 3 positive. So this is the angle that I'm looking for, pi over 3. Yeah, 1 over, sorry. Just scrolling, I'm losing myself here. Okay. Next one, we want the inverse cotangent of 1. So we're looking for an angle such that when I take the cotangent of that angle, which they named for me y, is going to be equal to 1. So dividing something by itself, that's the only way to get 1. So these are the easy ones because it's got to be our radical 2 over 2's. And we want it to be positive, which again means we have to be in quadrant 1. So that angle is going to be right here because that's where we're going to take a quotient, or get a quotient of 1, no matter which way we divide it. So here our y value has to be pi over 4. And one last one. So the arc cotangent of the cotangent of negative pi over 4. Very similar to what we did a few minutes ago. Again, these being opposite operations means they're going to cancel. So technically they should leave us with a negative pi over 4. Negative pi over 4 is where? So if positive pi over 4 is here, negative pi over 4, oops, I went too far. Negative pi over 4 is going to be here at 7 pi over 4, not in the range of angles that I'm looking at. So negative pi over 4, again, can't take this, which is the same as 7 pi over 4. Alright, but we can't take either one of those because they're not in the range. So what I'm going to look for then is an angle that is in range that has the same value for cotangent. So at negative pi over 4 or 7 pi over 4, our cotangent value, if I divide that x by that y, I'm going to get a negative 1. So now in the range of angles I'm allowed to choose from, where do I get that same value for cotangent is going to happen here. So our angle in range is going to be 3 pi over 4. So we're going to choose 3 pi over 4. And again, both of these or the cotangent for both is negative 1. Okay, so they have the same value for cotangent, but those other angles are not in range. We've got to pick the one that's in range and has that same value. Okay, now remember, the calculator is not going to give you any of these exact values. The calculator is only going to help you if you are looking for an approximation because the input is not on the unit circle. But your calculator can still be useful to verify, and some of this is tricky because you're not just looking at stuff on the unit circle. Now you're flipping things over and dividing, and so if you want to use your calculator to verify, then let's just verify number 10, okay? Because that's a lot going on in there. If I wanted to take the arc cotangent, remember that's the inverse cotangent, we put that in there, of the cotangent, put cotangent in there, of negative pi over 4. It's going to give me some decimal approximation. Now, according to what I have in my paper, that decimal approximation should be equal to 3 pi over 4. So if I type 3 pi over 4 in, I can see same decimal approximation. Now, if I would have stuck with the original, which was not in range, you're going to see if I put negative pi over 4 in, not the same answer. And if I converted that to 7 pi over 4, still not, over 4. 7 pi over 4 is not the same thing. Okay, so I need to make sure that I'm keeping the angle that's in range, and that's all going to work out if you use your calculator to verify. So still useful in that way. Okay, hopefully you've got enough. I made a whole mess of the notes here, but I'm hoping it makes sense to you, and hopefully you have your own little nicely highlighted pictures that you can use as reference moving forward. So every time you're trying to evaluate for your arc secant or inverse secant, you have your picture here to use. Or if it's arc cosecant, you have your picture here to use. You know exactly what range you're looking at for the inverse functions that you're dealing with. Okay? But as always, if you have any questions, need any extra help, feel free to reach out. Until next time, take care.